So in this talk, will be it's kind of a follow-up talk from one of the Ignite meetups, and what we are going to present is a framework that is based on Apache Ignite, which is focused on building reactive systems. So you can think of it as also a microarchitecture that is based on Apache Ignite. First, maybe a few words about the companies and the projects that we do. So the framework that I'm going to present, the approach that I'm going to present is actually a joint approach, joint effort from 3 companies. So the first one is Kubo, which is a European company that is focused on high-performance computing in private cloud environments. And this company basically is providing infrastructure to Obecto, which is the second company. And Obecto essentially is an innovation lab focused on AI and blockchain. And one of the Obecto projects, which is an algo trading platform, actually is the project that drives us to create this framework based on Apache Ignite. And the third company is Comrade Cooperative, which is a democratic organization focused on blockchain technologies. And this is the third organization that is contributing to the framework that I'm going to talk about and to the approach that we are using. And the main effort in this organization is around blockchain and around creating a consensus network for autonomous agents, which is called Cooperative. So now the question is, the first part of the presentation will be why doing another approach to reactive systems. So the reactive systems and reactive programming is something that is out there for quite long, and there are plenty of technologies that can be used to build such kind of systems. So the question is why we are introducing a new approach. So maybe before jumping to that, let's first have a quick overview of what reactive programming is and actually how data processing can be done by using the ideas of reactive programming. So essentially, the reactive programming is it's a programming with asynchronous streams. And in those kind of programming, what you do is, the way that you do computation is that you first specify a computational graph, and then you actually do the computation as the data flows through the graph. So let's now try to imagine one kind of a simple computational graph. So let's say that we have some sort of a data source. It could be a kind of a cloud storage, or it could be some sort of a enterprise service bus in the cloud. And then we'll have the first computational unit, which is some sort of a generator that will extract some data from that cloud storage or some sort of external data source. And then this generator will propagate the data through several processors, which are going to process the data. And then another processor, which let's call it aggregator, is going to aggregate the results from that processing. So essentially, this is a computational graph, but no computation is actually happening. We are just specifying what should be the computation as the data starts flowing from the data storage through the graph. When the computation starts, actually the computation starts in the reactive system. The computation starts when somebody requests the data that has to be computed. And in that case, let's imagine that we have a consumer that would like to consume the data from the aggregator. So the consumer engages the aggregator, which then engages the processors, which then engage the generator, and then the generator starts loading basically the data from the data cloud. Or is it kind of a sort of a subscription mechanism? We can have a WebSocket or some other messaging that can continuously push the data to the generator, or we can do it in some other way. It depends on the actual generator and the actual data. But in the end, in all the cases, what is happening is that the data starts flowing from the data source to the generator, then through the processors, and then to the aggregator, and finally it reaches the consumer. So what's interesting, like this is kind of a typical reactive programming flow, and it's something that is happening in all the systems that are implementing this programming concept. But what is actually interesting when we actually apply this concept to data processing? What is interesting is that quite often the actual processors will need access to some sort of external state, which can be quite heavy side, I would say, like especially if we do, like some big data processing or some sort of analysis. Another thing is that sometimes the messages that actually flows through the different units of work can become quite heavy as well. Like for example, if we are having some sort of a data processing that builds a data set by aggregating data from various sources, this data set might become quite large. And the other thing is that when we apply this data processing, especially to big data processing, quite often the different agents in the system or different actors, if we are using the actor model, might have to run on a different node. So the whole computational graph has to be clustered across multiple nodes. So in essence, this is the whole concept of reactive programming, and the important highlights here is that the systems, the reactive system, they have to be responsive, resilient, elastic, and message-driven. The other thing is that the things like propagation of failure and also kind of completion propagation when basically a stream exhausts its data source have to also forward through the computational graph in addition to the actual data. And the third thing is something quite important, especially for the big data processing, is that you might want to have a configurable data locality. So you can make sure that the actual unit of work is collocated with the data with a larger data data blob that is used in the computation. So this could be the state, or it could be the incoming package. So now the question is, okay, those kind of systems, there are plenty of tools that we can use to build such kind of system, and that's absolutely true. So all of those technologies, the way that I try to group some of them are in the several categories. So we have the actor frameworks like Akka and Dapper. So we have streaming technologies like Kafka and RabbitMQ. We have big data technologies like Apache Ignite, Flink, Spark, and something that it's relatively new compared to Spark and Akka, but still, it's the containers is a topic that we all know. It's quite hot in the last 5-6 years. So all of those technologies that can be combined and used to actually create such kind of systems. Also, those technologies, they quite often overlap in terms of features. Like, for example, the Akka framework, it also has streaming capabilities. And also it has clustering capabilities, which kind of overlaps with some of the features that are provided in Kubernetes and the projects around the Kubernetes ecosystem. On the other hand, we have the streaming technologies that also provide ways to collocate computation while we are subscribing to the streams. So all of those kind of projects, they overlap with each other on one hand. On the other hand, the different projects are focused on different, have different strengths. And usually when you have a kind of a large company, and I have been working with those kind of most of those technologies in the larger enterprises, it's always the obvious choice. So you combine them in the proper way. However, this choice usually comes with the learning curve for the developers on one hand, and on the other hand, more complicated operations and operations efforts. So now the question is what we do if we are kind of a smaller company, either a startup or like, for example, a small department in a large company. Usually you cannot afford really to start working with a very complicated stack. Of course, the cloud companies are something that it's a choice. You can use their managed services. However, they are kind of the costly option in some cases, and also are not always offering flexibility. So what we decided in that case was that instead of really trying to assemble more like enterprise architecture combining several technologies, what we decided to do is kind of do a step back and really try to figure out what we really need in order to build a reactive system, and how we can pick up the most amount of technologies in order to achieve what we want. And what we really focused on 4 key ingredients. So first, we really wanted to have a a platform that is focused on developer productivity. This is very important for the small teams and for the small companies and the startups, because the developers usually they are focused on a specific domain, and the ability to really to be able to kind of lower the learning curve, the technology learning curve, and focus on the actual domain that it's your business is really essential. Second thing is try to reduce the operations. So ideally, you have a no-ops platform which scales horizontally, and ideally, you have the flexibility to have a cloud agnostic model. And the third thing is the so-called 80-20 rule. So we would like to have a platform that really kind of provide out of the box the most important components for a reactive system, and provide a lot of default solutions rather than a lot of options for configuration. And the fourth thing is really to have a platform that can be easily integrated with the ecosystem. So we don't want to have kind of another silo or something like this, in order to be able to grow the software reactive system as the company grows, or as a product or the use cases grows. What we have based on those ideas, actually what we have created, we really, well, this is kind of a short code snippet that I just want to emphasize on a few aspects around productivity. So as you can see here, what we are showing, what I'm showing is a C# source code. So it's very important for us. It was very important really to have a platform that is language agnostic, so we can use the right language depending on the framework that has to be used for the specific domain that we want to implement. And in that case, what we want to do is really to use idiomatic expressions in order to reduce the learning curve. So we can see here that the streams, the reactive streams, actually they're represented as built-in as a built-in primitives from the language, and also the way that you basically yield data through the streams, and also that you propagate the things like completion and exception errors is also done idiomatically. So the code that we want to have is kind of a very simple, very concise expressions. So now the question is, okay, how we can achieve this? So how we can have kind of very idiomatic expressions and still have the scalability characteristics and the data processing characteristics for that platform. So what we decided actually to do is to combine basically two technologies. The first and the most important one is Apache Ignite. So we decided to actually use pick a single technology piece from the landscape and try to actually pick the most versatile one and try to actually extend it with the minimal, try actually to apply the minimal amount of extensions so we can achieve our goal. So why we decided to use Apache Ignite as a cornerstone for our architecture. So the first argument is the Swift's Army knife. So what we really see in Apache Ignite is that it has all many of the features that we really need: the in-memory computing, the scalable data storage, the persistence, and so on. And it's really packaged in a single piece without in a very configurable way. So that's why we call it kind of a Swiss Army knife. The second thing is the in-memory computing, of course, the persistence I mentioned, the easy integration. So the ability to have a thin client that can be easily ported into various languages was really important consideration for us. And the third thing is really the advanced clustering capabilities and the ability to really configure the data locality. This was something that comes built in in Ignite. So how we have actually structured the system. The way that we structured the system was that so what we wanted to have really is use the Apache Ignite as a fabric, as a medium, and then have a variety of actual units of work in terms of computation, or things that are going to happen outside of the Ignite cluster and can be implemented in a variety of languages. So the architecture of the backbone of the system, or the engine, or how we call it, the fabric, It's entirely based on Apache Ignite. So what we have is a bunch of Ignite nodes, then we have a bunch of stream caches, which contains the streaming graphs. Then we have several services. The stream orchestration service is a cluster singleton, which is really focused on the orchestration of the computational graphs. Then we have the actual stream data, where every stream is a different Ignite cache, which is partitioned across the cluster. We have stream management services, which are node singletons, which are ensuring that depending on the data locality configurations of the application, they're actually managing the data flow. And then we have transport services, which are basically propagating the data or the notifications or the events inside the cluster, outside of the cluster, to the computational unit. So the first important aspect is how we have achieved data locality. So the way that we achieve data locality is by using the continuous queries, which is one of the very good, cool features of Apache Ignite, I would say. So there are basically two interesting configurations here. Like the first configuration is where we would like to have locality to the actual stream item. So in that case, depending on the node that is used for creating or for storing the actual stream item or the actual message. So depending on the remote filter, we locate the node, and then we basically propagate the message through the stream manager on that node. The other option, of course, is when you want to have locality to something else, like for example the state of the agent or the computational unit. So in that case, we again use the continuous query, and then we use affinity call based on the node that holds the state of the actual computational unit, and we then locate again the appropriate stream manager. So by really using the continuous queries and the affinity calls, we are able really to configure based on configurations to implement the configurable data locality. The second aspect is after the actual message goes through reaches the stream manager, it has to go to the transport layer and has to be basically propagated to the actual unit of work that is going to do the actual computation. So in that case, all those units of work, or the programs, we call them agents essentially, but you can also view them as virtual actors. We have those agents implemented as containerized applications. So this was very important for us to be able to utilize containers in order to be able to integrate this kind of computation in other frameworks, like for example, algo trading frameworks or blockchain-related frameworks. So this is why it was really important for us to have the flexibility to actually use containers for holding or performing the actual computation. So those containers, the way that we orchestrate the containers and the Ignite node, we use Kubernetes for that. So what we have a Kubernetes pod for each of the Ignite nodes. They're configured with anti-affinity. So we can make sure that they're running on separate physical nodes with directly attached storage. Then we have affinity configuration that makes sure that the actual units of work, that we have a Kubernetes deployment for every unit of work that has affinity with every Ignite node. So depending on the actual data locality configurations, the unit of work that is going to be invoked when a specific message is delivered for a specific stream can have affinity with the data, with the node that contains the data, or with the node that contains the state. Like for example, if we say that the state is here and the stream item is here. How we do the scaling, which is a very important aspect in the reactive system. Well, in that case, what we decided to do is really to use again an ecosystem tool for that. So we are using Kubernetes event-driven autoscaler, which is an autoscaling operator that, based on certain metrics, scales up and down the deployment. So what we do is the actual transport layer. When we figure out what's the number of messages that have to be computed or kind of handled by a specific agent, we can use the heuristics of the external scaler of the GET operator to actually increase or reduce the number of pods. The other thing is that here you can see the language that we want to support for the different projects that we do, and this was really the major design decision behind using containers and combining actually Apache Ignite with Kubernetes here. So then after we have figured out, okay, how we have structured the actual fabric, how we have structured the actual Unity forks, how we operate the system, now the question is, okay, how we do or how we implement the message delivery by using Apache Ignite. So the way that we do it is entirely, again, utilizing Apache Ignite features. So what we have here, let's say that we have agent Alice and agent Bob, which are kind of two agents which are doing a specific computation. And let's say that agent Bob is subscribed to a data from agent Alice. So in that case, what's happening is that the agent Alice computes or generates some sort of data. Then we have to use the Apache Ignite binary serializer to actually convert it into a cross-platform binary format. So this is actually something that we have quite challenges. So we needed to contribute a couple of fixes in the different, especially in the thin clients. But what we really think is that that the binary serializer that Apache Ignite have is kind of a very good kind of approach and the ability really to actually convert the data to a binary format, for a cross-platform binary format, and then deal with the binary only with binary format. Through the whole orchestration process was again something that was very handy, and it saved us a lot of it saves us evolving other technologies and a lot of effort. So basically, every stream item is converted to a binary format, and then through the twin client is added to a specific partition, a specific cache. So when the specific partition of the Ignite cache that holds this data is referred, and when the data is saved in the specific permission, what we have is cache events which are propagated through bounded channels to the stream manager, and then the stream manager through bounded channels again propagates those notifications, those events to the transport layer. So it's very important to note that everything that's happening here is again based on the Kotlin reactive streams. So and there are reactive streams. So everything has a non-blocking back pressure, and essentially when the event reaches the transport, basically the event is buffered, and then using the Cooperative server, we notify Bob that there is an event which is waiting for him. So we are basically buffering the event here, and actual notification that is sent to the gRPC is with a fixed memory footprint. It's kind of just an ID. So in essence, from an agent perspective, all the flow control is actually handled and implemented within Ignite, and basically any sort of message is already buffered. So what's happening then is Bob receives notification, and then by using the thin client and the atomic cache operation, it reserves the notification. So that makes sure that when the specific instance of Bob reserves notification, we can have a parallel consumer, so we can have multiple instances of Bob that are consuming notifications in parallel. Then the actual message is taken from the partition cache, which can be kind of like hundreds of megabytes. Then it's processed here in Bob, and then when the processing completes, the notification is consumed. And then the last aspect that I would like to talk about is the security model. So the security model that we have implemented is based on object capabilities. And this is a security model that relies on object references. It's very suitable for multi-agent programming and also for actor systems. And essentially how the whole security is implemented, how it works. So the idea of the references and the object capabilities is that you can call or you can send a message from one agent or to another only if you have a reference to that agent. And the references, they can be obtained through two ways. Like the first one is through parenthood. So basically, if we have a agent Alice that that starts an agent Charlie, then Alice receives a reference to Charlie. Then Alice can, like if we imagine that Alice beforehand has a reference to Bob, what Alice can do is Alice can send this reference to the reference for Charlie. It can send it to Bob. So now Bob knows Charlie and can call or send a message to Charlie. So the same applies to all of the to doing a call or subscribing or receiving an item from a subscription. So all of the operations that can be done between the agents are actually logically done in this way. Now it's very important to emphasize that this communication here is a logical communication. So what happens under the hood is, basically the Bob, Charlie, and Alice, they don't have direct visibility in terms of networking to each other. For everything, they rely on the fabric. And here, in a sense, we can think of the fabric as a service mesh or as a message broker that acts as a medium and for all of the interactions between different agents. And in the end, the unforgeability and the privacy of the references is actually implemented based on the Ignite security mechanisms. So what we have here is that when every agent, so every pod, when it initiates connection to the Ignite node, it is using the authentication authorization capabilities of Ignite. So what we do here is every Ignite pod, it has a secret kind of a password that is distributed through Kubernetes to both the Ignite node and the actual agent. Then when the thin client authenticates with the Ignite node, security context is basically created for that client, and then the custom grid security processor is performing authorization step in which it checks whether the specific Ignite node it has. On one hand, it checks whether the specific thin client it has access to the specific caches, and the more interesting case is when Alice really wants to read the message that was sent to him to her from Bob or Charlie, for example. In that case, Alice will need access to the caches that are owned by Charlie and Bob, and in that case, what we do here, we are granting a temporal access to that cache based on whether there is notification that Alice has received or not for that specific item or for that specific cache that is holding the item. And then the underlying security model, what we basically have is we're using Kubernetes with for managing and distributing the keys and the secrets, and also for ensuring the network access and ensuring that the actual pods, they don't have network visibility within each other, and they only have visibility to the actual Ignite nodes. So yeah, that's it. I think that I managed to kind of do it in 30 minutes. Just a few more words. So we have everything that we have done for that project is open source. So the name of the project and the architectural project is called Pepper. So we can browse the Pepper repo in GitHub. Yeah, please check it out. Of course, there are some pieces of it that are still work in progress, but I think it's quite interesting place where you can learn a lot of things about Ignite and also really see how we are using it. Then I also invite you to check out the Apocryph blockchain project that we are working on. It's fully based on Pepper, and it's a kind of you can think of it as an extension to Pepper that adds the consensus network between the different agents. So the agent that you can run on Pepper, actually you can use the same agents to run them in Apocryph, and you have the built-in consensus for that. Also, you can check the Apocryph network website for more information about the project. And also, yeah, please, if you are interested, join us in our Discord channel. The Discord channel, there we have a lot of discussions around blockchain and also around Pepper and the reactive systems in general. So yeah, that's it from my side.
Thank you, Branimir. And you still have a few minutes, and please type your questions in the chat, or in the QA chat. While we have time, probably you can tell us a bit about your open source activities now. So what are your plans?
Absolutely. So currently our main focus are on those two projects, Pepper and Apocryph. So what we are doing is we are having another iteration on Pepper, where we are going to introduce stabilize a few of the implementations that I have discussed around, especially around security and sandboxing. We are working actually on a new runtime for Pepper and a new way to actually structure the application. And this runtime is also going to support the sandboxing mechanism of the agent that we're going to use in Apocryph. Also, our efforts around Apocryph are also quite solid there. We are able to have a DevNet where we are testing actually our consensus, and also we are kind of planning to do a bit more performance testing that is also going to to lead back to also some more improvement in Pepper as well, and benchmarks. And these are the two projects that we are really fully focused on them, and they're completely open source projects. In Pepper, we are also planning to open source a few more pieces from Obecto around using Jupyter notebooks to work with the reactive systems and manage them. So yeah, quite exciting time for us, and yeah, I hope that what we do might be also usable and handy. Some other people might have find it handy as well.
Great. In that case, I hope that we will see you on our virtual meetup with something new about also using Ignite.
I see one question from Noel Diaz.
Yeah, that's about serverless. Yes, please.
Yeah, that's a great question actually. So the way that we the question is how is that what you have implemented serverless? So the idea here is that so what I have described, you can think of it that the fabric side of the thing, so everything that is happening in these Ignite nodes is just a fabric component that you can deploy, and we are also having a Kubernetes operator that scales it through Kubernetes. And then the actual programming that you're actually doing is by just creating the actual agent, and then the everything around the agents, the scaling of the agents from 0 to the number of instances and everything like this is not configured. It's not necessary to be configured by a developer. It's automatically handled by the pod, by the fabric pod, and essentially by the framework. So what we have is we have the gather operator, which is not configured by the developer. It's purely it purely calculates the actual number of pods that you should have based on the actual gRPC metrics. The other thing is that in addition to the agent that looks like something like this, we also have a support for Azure Functions. So the developer can opt in to either use a container and kind of integrate its agent with the third-party framework, or We have also out-of-the-box support for Azure Functions, which is just not confuse the Azure Functions with the Azure Cloud. It's just a bad naming for Microsoft, but Azure Functions actually is an open source project for serverless computing. So we have an extension for Azure Functions. So the developer can opt in that instead of actually creating a fully featured application, which is kind of more like a Knative way of serverless, if you can also, the developer can also opt in to create a pure function, a simple function, which you like just annotate, have something like this and just annotate it with the appropriate attributes, and then have this function directly deployed to the Pepper fabric. So we have this kind of Azure Function extension as well. So this is why we refer to this as a serverless, because on one hand, all of the scalability and all of the scalability options are automatic. So the developer doesn't need to actually configure the scalars or do anything like this. And on the other hand, we also have a support for serverless frameworks like, for example, Azure Function, which is the one that we have currently.
Thank you. And we have one more quick question. I've noticed that you use Python thin client, asked Ivan. Have you heard about new version or have you tried it?
Well, yeah, that's an interesting question. So, well, we haven't. Not sure how recent is the new version. We have
last month. That's last month.
Last month. So not sure if you have used the really latest version, but we have used the one for 2.8. And yeah, we had a couple of problems with it. We had a few contributions around the binary serialization and through Apache actually. I'm not sure if we have contributed them, but yeah, if it's from last month, maybe we should. If it's from the beginning, if it's from May, we haven't used it, but if it's from April.
So in that case, you should join us a little bit later because Ivan will tell you about that updates for the Python client because he's one of the developers.
Oh, great.
That was a spoiler, okay. So thank you, Branimir. Guys, you can meet Branimir in a hall in the Q&A room. And we are moving further.